Dear listeners, my name is Margarita and I would like to present you the results of our work on the outlier detection based on the Chebyshev inequality. Let us consider the set of observations where each observation is described only by its mean and its standard deviation. This situation, when data has such a type, is actually common for natural and technical tasks. We do not know the amount of observations as well. And the main task we are dealing with is to propose a method of outlier detection for data of such type and thus to apply it to real data collected as astronomical observations. Before we start solving the main task, we need to define what an outlier itself is. However, there is no definition which can satisfy any case. One of the most common definitions is presented on the slide. An outlying observation or outlier is one that deviates markedly from the other members in the sample in which it occurs. A funny picture on the slide illustrates the definition to some extent. However, this picture also lets us understand that in each particular case, an outlier will have its special features. For example, if we talk about astronomical observations, an outlier in such a set will have means and deviations considerably different from the ones belonging to the observations considered to be true. Developing of our method starts with reviewing the existing Gauss-Chebyshev type inequalities. Their idea is to guarantee that a random variable mostly takes a value close to its mean. To be precise, they guarantee that only a certain fraction of values can be more than a certain distance from the mean. Well, we have observed Gauss, Chebyshev and Vysochansky-Petunin inequalities and chose the Chebyshev inequality because it is suitable for a wide class of probability distributions and it doesn't require the variable to be distributed unimodally. So, as we have already discussed, we have data represented as pairs of means and their standard deviations. Actually, if we are talking about real data we are going to deal with, these pairs are not the observations themselves, but each of them describes a group of observations obtained at approximately one point in time. What is crucial is that we do not possess any other initial data. For example, the amount of these observations in each group and their own characteristics are unavailable. In any case, from now, saying the word observation, we mean a mean standard deviation pair, which is at our disposal. So, applying Chebyshev inequality to these observations, we can introduce so-called confidence intervals. Well, the figure on the slide corresponds to the meaning of this concept. For example, here, solid black parts, like these, correspond to the mean standard deviation pairs, while dotted gray lines, like these, describe the confidence intervals, though with equal perimeter k for each pair here on the figure. Well, it is easy to check that the probabilities of belonging of random variable to the confidence interval is it has the form as presented on the slide, like this. And now let us consider the problem of outlier detection as the problem of hypothesis testing. Having denoted prior probabilities, here, we introduce the Bayesian risk function, which has the form according to the one pointed on the slide. Here alpha, or probability of H1 given H0, is the probability of type 1 error, while beta is the probability of type 2 error, and C0 and C1 are the given error costs. Our aim is to minimize the function on K0 and K1, and applying the Chebyshev inequality we get the constraints on alpha and beta, and further the upper bound of the Bayesian risk function. However, we can see that the task of the unconstrained minimization has no sense. On the other hand, it is quite natural to consider this problem only in case of non-intersecting confidence intervals, like here. Returning to the already shown figure, as we have already done actually, from here we can get a simple condition of non-intersecting. For example, for the observations obtained at T0 and T1, points in time. It is as pointed on the slide like this. It is really corresponding to what we can see from this figure. Well, we can even simplify the task if we take the equal k0 and k1 values equal to some k value, for example. And actually, this is what we have done in this work. Doing this, we obtain an optimal k, or it is better to say k star value, which, as we remember, is needed for estimating the errors. This value is rather rough because of all the assumptions we have made, for example, this assumption. However, we are going to show that it is enough for successful data processing. Everything already discussed leads us to describing the main idea of the algorithm. Let us consider two adjacent observations, for example, the one which occurred at the ith and the one which occurred at the i+1th point in time. For these observations, we can find the corresponding k star value in accordance with the above formulas. If it is greater than some predefined threshold k bar value, we decide that an anomaly has occurred. Actually, the word anomaly means not only the outliers which we are dealing with in this work, but it also can mean so-called shifts. In any case, we are not dealing with the other types of anomalies in this work. As for threshold value selection, we suggest to take k bar equal to 2. According to all the output above, it means that the errors of type 1 and type 2 are not greater than 1/4, which is usually enough for successful processing. It is necessary to prove that the proposed algorithm works correctly not only from theoretical, but also from practical point of view. For that, we have to model test data where the outliers are exactly known. In this case, we can judge whether the algorithm processes the data correctly or not. On the other hand, as we are interested in solving the particular task, this data should have similar structure to which the real data has. We are working with data of lunar laser ranging, and at the moment we are not actually going to discuss the real data nature in detail, but what is important about real data is that real data turns out to be presented as a sequence of segments which obey different distributions which are usually unknown. These segments are separated from the neighboring ones by pronounced shifts. This is another type of anomaly which, as I have already said, we are not going to deal with in this work. Also, each segment is contaminated with outliers. The number of outliers accounts to 2 to 3% of total amount of observations. And, as we also have already mentioned, the outliers should have means and standard deviations considerably different from the ones belonging to the observations we consider to be regular. After we have determined what we actually expect to get, we proceed to a detailed analysis of real data. First of all, based on the visual assessment, we manually divide real data into segments, at the same moment removing outlier-like looking observations. As soon as the data is divided into segments, we make an attempt to match the distributions and their parameters with the segments, so that they can describe the real data in the best way. We actually chose these distributions for the means, and these distributions were chosen for describing the standard deviations of these means. The choice of distribution was made, first of all, according to quality of their fit in real data. For each segment, we chose the best fitting distribution pair by applying chi-square test. We fixed this pair and its parameters, and on the slide you can see the table which represents how many examples of different pairs were met in percentage. So, here are the basic rules for generating data. First of all, we randomly choose the number of observations in the segment. Secondly, according to the results on fractions of different distribution pairs, we choose a distribution pair randomly. The parameter value set, however, is not generated, but randomly chosen from the sets of the same pairs in the real data segments. After we have generated a segment, we contaminate it with the outliers, which amount accounts to 2 to 3% of total amount of observations. As we have already mentioned, the outliers should have considerably different means and standard deviations. And finally, we have to concatenate all the generated segments. Well, the results of the experiments were quite successful, I think. For example, here on the slide you can see a figure visualizing processing the model data with the algorithm. The observations considered to be regular are gray-colored, like this, while the observations which were considered to be outliers and which have been detected are black-colored, like this. And actually, these were the observations which we supposed to be outliers initially. Well, in this particular case, the algorithm worked 100% correctly. There are neither type 1 nor type 2 errors. And anyway, visual analysis, of course, is not enough. Conducting the experiments with different Monte Carlo cycles and segment numbers, we found so-called probabilities of detection. Here we can see the formula for this probability, and also probability of false alarm. Here is the formula. And these probabilities can show us whether the method is reliable or not. The results were pretty good, I think. For example, as we can see on the slide, for Monte Carlo cycle numbers equal to 1000 in different numbers of segments, we got probability of detection approximately equal to 0.99, while the probability of false alarm was approximately equal to 0, with the margin of error, of course. But anyway, these results are unexpectedly good, because as we can remember, the Chebyshev upper bound is equal to 1/4. After all, we can finally proceed to applying the proposed algorithm to real data. Here on the slide you can see the figures illustrating the results of the procedure on absolutely real astronomical data collected in different observatories. The observations which are considered to be true are gray-colored again, like this, for example, and the outliers are black-colored, like this. Well, the main feature of the real data is that we never know if an observation is an outlier or not. So we have no, let's say, correct answer to compare our solution with. Thus we have two ways to analyze the results: visual analysis and expert review. Analyzing the results visually, we see that some observations which could be considered as outliers are indeed detected. For example, these observations which I have already shown, there is no doubt, as for me, there is no doubt that these observations are outliers. Though not each or not each of the observations which have some different characteristics has been detected. For example, as for me, just from the visual point of view, let's say these observations seem a bit different from what we can see close to these observations. I have no idea why they were not detected, but for some reason they were not. Probably they are not so let's say significantly different. Like on the other hand, there are some observations which for some reasons were detected as outliers, though they are not maybe visually similar to outliers. For example, the observations here or here, just visually as for me there is no reason to detect them, though for some reason they were detected. That means that the difference between these observations and the neighboring observations was found by the algorithm, which is quite interesting. Well, from the analysis of previous work made on outlier detection in this data, and from the expert review, we managed to understand that the results which we got at least resemble what we were supposed to get. So, here are conclusions. First of all, we managed to apply a classical probability tool to a new task of outlier detection in stream data described as pairs of features, means and standard deviations. Secondly, after applying rather natural conditions, we managed to propose a low complexity algorithm. Then, we have worked hard to model real-life data, including real data analysis, and we conducted an experiment proving the validity of the proposed algorithm. Next, we managed to observe rather good performance on real data while applying the proposed algorithm. However, even this performance could be improved. As we remember, the Chebyshev inequality we used is applicable to a wide class of distributions. However, if we know more about our data, for example, we know that our data is distributed unimodally or even probably normally, we can use Gauss or Vysochansky-Petunin inequalities. And eventually we expect successful application of this algorithm not only to astronomical tasks, but to a wide class of tasks in other fields, for example, nature and technical tasks, where this kind of data presented as pairs of means and standard deviations can be dealt with quite often.